So in our third video on diffraction in Young's double slit experiment, we are going to be finding wavelengths and the angle of diffraction under experimental conditions. Now, in experimental settings, it is often difficult to measure the angle of diffraction because this angle is very small relative to a point that is very far away from the two slits. Now, if I look at this here, this looks very familiar to what we were looking at before. We have our triangle here to figure out my wavelength, to figure out what is the wavelength or how many nodes we have. If we knew what the wavelength is, we could figure out how many nodes away this point is, or just to figure out the distance with wavelength or my angle of diffraction. But we're going to be focusing on a new variable here, where we have the distance between my point, which is my node or antinode, and my central bright node. So we end up getting a new formula. When we introduce this new formula, we can create this formula. So my wavelength is equal to my x, which is my distance between nodes, or distance from my bright node to my antinode, multiplied by my distance right here, okay, between my slits. And we're going to divide that by my number of nodes, and divided by L, which is this distance here. Okay? So in other words, if we want to find the nodes instead of my antinodes, remember nodes are in half intervals, so we're going to be going that way. All right, so here's our first question. A student measuring the wavelength of light emitted by a krypton gas sample directs the light through two slits separated by 0.264 millimeters. An interference pattern is created on a screen 3 meters from the slits, and the distance between the second bright, which is the second antinode, and the fringe of the central antinode is 1.18 centimeters. What is one of the wavelengths of the light emitted by the krypton gas? So now given all of this, we are given my length from the screen to the slits is right here. We know my distance between my nodes, okay? And my distance between my nodes, and this is my distance between my slits here, my distance between my nodes, and how many nodes it is. So using that, we're going to use the formula we just learned today, which is my wavelength is equal to my distance between my central node and the node we want, multiplied by my distance between my slits, divided by my number of nodes, and also divided by my distance. So altogether, when we do this and we do our unit cancellation, we're left with only meters, which ends up giving me a wavelength of 5.2 times 10 to the negative 7 meters. So here are 3 practice problems that I would like you guys to spend 5 minutes doing. Now that you're done those, we're going to go into a little bit more information. So the concentric circles cut into a CD when it is made behave as diffraction gratings. So the rainbow pattern we see when we look at a CD, if you guys still look at CDs, I'm not sure, this is more when I was a teenager or kid, you see an interference pattern caused by diffraction. That's the rainbow. So a diffraction grating is a sheet of glass etched with large number of parallel lines. When light is incident on the grating, each line slit acts as an individual light source, which gives us these bright things, so nodes and antinodes. And that is called a diffraction grating. Now, Young's experiment only used 2 small point sources. Remember, from Huygens, we said each wave will have many point sources. And then as soon as we make 2 tiny slits, those become new point sources of the light, and then those waves interact with each other to give us a diffraction grating. So a diffraction grating has a very large number of, that gives us an interference pattern, not a diffraction grating with Huygens. So a diffraction grating has a very large number of equally spaced parallel lines that act as individual light sources. When light is incident on a multi-slit diffraction grating, an interference pattern similar to that of a double slit is produced on a distant screen, but there are several key differences. First, The large number of lines in a diffraction grating can deliver more light energy to a distant screen, increasing brightness of the interference pattern, and so on. Second, the antinodal bright fringes are more defined, being sharper and narrower. And third, when the light separation is very small, the separation between the lines D is inversely proportional to the distance between the fringes. This interference pattern is using this here. So here, this is my distance between my gradient lines. Here is my distances between my fringes or nodes. Here we have my wavelength, here we have my nodes, and here is the distance between the screen and my bisector, or the distance of that bisector. Okay? So, therefore, the extremely small separation distances between lines and gratings will cause an increase in separation between the fringes in the pattern. For these reasons, a diffraction grating is a very precise apparatus for investigating wavelengths of light. So, diffraction gratings are defined as the number of lines per centimeter. Notice how this isn't per meter, it is lines per centimeter. So, these are not equal to D. So, if I have 5,000 lines per centimeter, that is not the same thing as 5,000 centimeters. Okay, it's how many lines per centimeter. So, if I want to figure out, I have to go to the -1, or go 1 divided by this, right? I have to take the reciprocal and convert it to meters, so we use this key on our TI-84s or TI-83s. So I go 1 divided by that, and that tells me actually the distance between each line. Now, we have right here a diffraction grating of 1,000 lines per centimeter. When the light passes through the grating, interferes with the pattern produced on a screen 4 meters away. This first order bright fringe is 19.2 centimeters from the central antinode. What is the wavelength and the color of the light? So first here, we know my distance is, remember, we have to go 1 divided by that and then convert it to meters per line. So we have to take the reciprocal of this and then convert it to meters, so we times it by, or we divide it by 100. Okay, so if we change this, we have to change this to meters, and then we take the reciprocal. Now, we have 19.2 centimeters, which is 1.92 times 10 to the -1 meters, is my distance between each node there. Okay, from the bright central node to my first antinode. And we're looking at my first antinode because it's the first bright, and we know my length from screens is going to be 4 meters. So now we plug these all in using this formula, and we end up getting a total of 480 nanometers, because times 10 to the -7, and we just convert that to nanometers. So now I want you guys to do these questions here. So our last part here is going to deal with polarization. Many of you guys have heard of polarization, and you have polarized sunglasses and stuff like that. Now we're going to explain what exactly is polarization. Well, Young's double-slit experiment had an interference pattern in general and provided strong evidence that light does exhibit wave properties. However, people were not sure. Were these transverse or longitudinal? Well, polarization, as soon as we use polarization, this will tell us that waves are indeed transverse, crest and trough, and not longitudinal. So what is polarization? Polarization is the production of a state in which a plane of either of electric field for each electromagnetic wave occurs in only one direction. Okay? So we're going to make it so it only happens in one direction, not both. So here, let's look at this. We have a vertical polarizer, which allows only some of the light to come through. Here the light's going in all directions. So if we have the vertical polarizer, the only light rays that are allowed to come through or propagate through are my vertical. Then all of a sudden I have a horizontal. Now the horizontal prevents these vertical going through, so then we have absolutely no waves. So I strongly suggest you guys to check these out with polarized sunglasses if you have two pairs. You take one and you put them 90 degrees and see what happens. because we only have the polarization one way, so some light gets through our eyes, but not much. But then when we turn them, and these slits are going both ways, so these are perpendicular, all of a sudden this area here, no light comes through, which is really kind of cool. And that proves that waves are, in fact, transverse and not longitudinal.